Okay, so I went through the week 4 quiz for strengths, and I previewed a quiz so that I could get the problem statements and random variables like you all have. And I'm just going to work this through cold turkey and we will see what happens. But I want you to be able to see how to, what I'm looking for. And several of these were straight off your homework assignments, which is why I picked them, because I thought it would be pretty straightforward. Okay, so we have 3 rods. There's no strain, so we don't have any internal strain or stress yet. And we are going to apply a load P. I can see it's symmetric. It's applied at P. The change in length 1. Okay, so my delta of 1 is 2.43 inches. Determine the strain if the original length is. So strain is change in length over length. So I gave you the strain. I gave you the original length of 78.3 inches. So the strain of rod 1 is 2.43, 78.3 divided by, and I get 0.0031. 1, 2, 3. Okay, and it says to enter it to the thousandths of an inch. So 0.003. Really, this class boils down to, do you understand the definitions? Okay, when I say there is no strain, our strain is starting at 0. Change in length, I have to understand that is length final minus length initial. Strain, I have to understand strain is just change in length over length. Okay, I have a rigid bar. It's supported by 2 bars as shown. There is no strain in the vertical bars before loading. After I apply the load P, the normal strain in rod 1 is negative because it's in compression. Okay, so I have a strain in rod 1 of negative 1991 micro strain. So that's times 10 to the negative 6 to get it back into not micro. Determine the downward displacement of point D. That's my load, where the load is applied. So here we have similar triangles. It doesn't even matter how long these are because that comes out as just the ratio. So if I can find this delta of this rod, then I can use similar triangles to find this. Well, I have an original length of 2.2. So strain equals delta over L. Delta equals strain times L. So I have my strain, and I have my length. And I get 0.00438 meters per meter. Okay, so that's my delta. That's my delta at B. Now I want to find delta at D. So I have delta at B is to L as delta at D is to 3.5 L. And the L's go away. So my delta D is 3.5 times 0.00438. So I have a delta at D of 0.153 going down. Downwards. So that's going to be my positive into the hundredths place, 0.05. In millimeters. Is that what that says? I can't read. Okay, so let me step up, back up, okay, because I found this in terms of, well, it doesn't really matter. It's whether I use meters or millimeters. Anyways, that's how you find it. Okay. When an axial load is applied at the ends, the total elongation of the bar between A and C, so delta total, is 0.16 inches, and I know that that's delta A to B plus delta B to C. If the segment of the normal strain in segment 2, so our normal strain is 1,328 times 10 to the negative 6 micros. Determine the elongation of segment 2. So none of this other stuff even matters. If I'm given the normal strain and I want to find the elongation, I know that strain is change in length over original length. I'm given strain of the second segment, 1328 times 10 to the negative 6 equals the elongation, that's my change in length, and my original length is 2 times 59. So I just multiply that out and I get delta. Okay, determine the internal normal force at C. Okay, here's point C. So I know if I cut it at C, it doesn't matter whether I come from the left or from the right. Well, if I come from the left and I cover that up, I'm going to have to find my reaction. I don't really want to do that. If I'm coming from the right, I can just look at this, and I know that I have P cosine theta and my internal normal. So when I sum forces, then I have negative N minus P cosine theta equals 0. So my normal force is negative P cosine theta. So I can take negative 131 cosine 67. And that's my answer. Negative 51.19. That's it. Next one. Keep on moving. For the following bar with a diameter of 4.2 inches, determine the normal stress for segment CD. So I want to know the stress here. Stress is P over A. Okay, so I have to find the internal force. So I draw my little free body diagram, and I have 3 times 190.2. And then if I'm in here, I also have to look at this. So let's come down a bit farther. We're cutting it right here. I have 8 times 190.2. And then I'm going to assume tension. So I have my internal force from C to D. Sum force C to D to the right is positive. So I get negative FCD minus 8 times 190.2 plus 3 times 190.2 equals 0. So FCD has to equal, make that positive. So I have a negative 8 times that and a 3 times that, so it's going to be 5, 190.2. FCD is 951 negative. And that's going to be in units of kips. And now if I want the stress, stress equals force over area. So I have negative 951 over, I'm given inches. So pi over 4, 4.2 squared. So I have 951, and then I have pi as a number, 4 divided by 4.2 times 4.2 times, divided by, and I get my stress is negative 68.642. Okay, compression is negative, so I have to enter negative 68 as a whole number. Negative 69. That's my internal stress. Okay, what most of you all are missing is you're not doing this step to find the internal force. You're just grabbing random numbers. Determine the maximum allowable force P. So I need to find out what is P. That can be applied if each nail, okay, so I'm looking at shear. It has a diameter and can withstand an average shear stress. Okay, so I have to understand that shear stress is P over A, which is really V over A. So as I'm pulling P, then these nails here are having to resist this force that's axial, but it acts parallel to their cross section. And I have 1, 2, 3, 4, 5, 6, 7, 8. I have 9 nails. And I can see it's in single shear. There's just one plane. So I know that my stress is going to be that shear force over 9A because I have 9 areas. So determine the maximum P. Well, V equals P that can be applied if each nail has a diameter and can withstand. So shear equals tau times 9A. And I have 53.4 mega times 10 to the 6th pascals, Newton per meter squared. And area, pi over 4.01 squared because I'm using meters. So I take 10 millimeters, doink, 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 and I have 0.01 meters. So I'm working in newtons and meters squared. So when I square this, my meters squared will come out and I'll be left with newtons. And I have to multiply by 9 because I actually have 9 of those things. So we have 53.4 times 10 to the 6th. Pi as a number, 4 divided by 0.01 times, 0.01 times, 9 times, that's how much area we have times, and I'm left with a shear of 37,746, which equals P. And it says enter it in kilonewtons. I've worked everything in newtons because I went to pascals, so I'm going to divide that by 1,000, and I get 37.7 kilonewtons. And it says as a whole number, so 38. Okay. A 16.5 inch squared bar is shown. So I don't know what the specific base and height are, but I know that my area, oops, you guys can't see, area is 16.5 inches squared. Determine the maximum force P that can be applied without exceeding shear of 272 on a plane cut at 29 degrees. Okay, so if I have a plane and I'm going to cut it at 29 degrees, okay, I can either look at this plane or I could go back and look at from the right and look at this plane. So I have 29 degrees, okay, and I know that I'm going to have a normal force and a shear force on this plane, and it's coming from this force P. Okay, so I am looking at going from my y-axis, going counterclockwise to this plane. So I'm going from the x-axis, I'm going counterclockwise to that plane. So here's my normal. So here's P. Here's my normal, and here's my shear. So if the shear stress maximum is 272 psi, and I know that on this plane I have a shear that is a function of this P, but now we're at an angle, shear stress is V over A. So the first thing I have to do is find this shear. Well, we can think of statics. We have vector, tip to tail, so V is sine. So sine 29 equals my shear. So my shear force is P sine 29, and I had a P of, that's what I'm trying to find. So that's my relationship. My area, because I've cut it at this angle, it's increased it. And it's increased it V over 16.5 divided by cosine 29. So I get 272, enter. I get 16.5, 29 cosine divided by, so that did increase it. Now I cross multiply, and I get that a shear of 5131 is the limiting shear. And now I can go back up here, 5131 equals P sine 29, divide, 29 sine divided by, that tells me that the load is limited to 10,584, and I want it as a whole number. So there's the load, the maximum load I can have, so that when I'm looking at a plane at 29 degrees, it would develop a shear force of this. And if I have a shear force of this, that is when I look at yielding, this is when the yielding would occur. And I think that's it.